Last time we taught a machine to see our own little convolutional net learned cats from dogs and clawed its way up to about 91%. Respectable. We built every filter from scratch, but here's a secret the pros use every single day. You almost never start from scratch. Somebody already trained a vision network on a million images. So this episode we stay in the same place on our pipeline, the build stage, but we pull a brilliant trick. Instead of building filters, we reuse them. Then we'll slip into train to fine tune. This is transfer learning. Remember where we landed? A from scratch CNN, 91% on cats versus dogs, good for a first model, but a network that has already seen a million pictures. It doesn't start at zero, it starts way up the mountain. We're going to stand on its shoulders. Same build, stop on the pipeline, brand new trick. Instead of stacking our own convolutions, we grab a network that was trained on ImageNet, 1,000 categories, over a million labeled photos, months of compute handed to us for free. That trained network is called the backbone. Why does borrowing even work? Because the early layers of any vision network learn the same universal things: edges, corners, color blobs, textures. A diagonal edge looks like a diagonal edge whether it's on a cat, a car, or a coffee cup. That low-level knowledge transfers. We don't need to relearn what an edge is. So here's the move. We freeze the backbone, lock every weight so training can't touch it, and we bolt a fresh tiny head onto the end. The backbone stays the expert eye, the head is the only new thing, and it learns your classes, cats and dogs in our case. But the backbone hands us a stack of feature maps, a little grid for every channel. Our head wants one flat vector per image. The bridge is global average pooling. Take each feature map, average it down to a single number. A 7x7 grid becomes one value. Hundreds of feature maps become one neat vector. No flattening, no explosion of parameters. Now we train, but only the head. The backbone is frozen, so almost nothing is changing. That makes this pass fast, stable, and cheap. We're fitting a handful of weights, not millions. In 5 epochs, the head already knows cats from dogs, riding on borrowed vision. That's stage 1. Stage 2 is fine-tuning. We unfreeze the top of the backbone, just the last block, the most specialized layers. And we keep training, but gently, a tiny learning rate, so we nudge those expert filters toward our data instead of smashing them. The bottom stays frozen, the top gets a polish. One rule you cannot skip: preprocess input. MobileNet was trained on images scaled a very specific way, pixels mapped into -1:1. If you feed it raw 0 to 255 pixels, the backbone sees garbage and your accuracy tanks. Match the preprocessing the backbone was born with. Get that right, and you go from 91% to 98%. Classification tells us what is in the picture. Next episode, we ask where. Let's read the file. 2 pages. Page 1 loads the data, grabs the frozen backbone, and builds our new head. Page 2 does the work. Train the head, then unfreeze the top and fine-tune. 2 pages, the same 2-stage story we just told. Top of the file, imports and the data. We pull in TensorFlow, Keras, and crucially MobileNet v2 plus its matching preprocess input from keras.applications.mobilenet v2. Then we load the cats versus dogs images at 160 by 160 with image dataset from directory, batched, the train folder and the val folder. Each has its own dataset. Now the data pipeline. We map preprocess input over both datasets. That's the negative 1:1 rescaling I warned you about. Applied right here so every image matches what MobileNet expects. Then cache and prefetch so the GPU never waits on disk. Here's the heart of it, the backbone. MobileNet v2 include top false, drop ImageNet's 1000 class classifier, we only want the feature extractor, and weights DOS ImageNet to download those pre-trained weights. Then the one line that defines transfer learning: base, trainable, false, frozen solid. The new head built with the functional API, inputs flow through the frozen base in inference mode into global average pooling 2D. That's our grid to vector bridge. Then drop out for a little regularization, then a single dense unit with a sigmoid, one output, a probability between 0 and 1, dog or not. Page 2 opens by training the head, compile with Adam at a normal learning rate, plain binary cross entropy. Our dense already has a sigmoid, so the output is a probability, not a logit, and binary accuracy as the metric. 5 epochs. Because the base is frozen, this flies, and you'll see validation accuracy land around 97%. Next, fine tuning. We flip base, trainable null true, then walk the layers and refreeze everything except the last block. Fine tune at keeps the bottom locked. We only want to touch the most specialized top end filters. Recompile, and this is the part people forget. Changing trainable flags does nothing until you recompile. We use the same loss, but add them with a tiny learning rate, 10 to the minus 5, 100 times smaller. Gentle nudges, not sledgehammers. Fit again for a few more epochs, picking up the epoch count where the head left off. Now a few 100,000 of the top weights are adjusting to cats and dogs specifically. Validation accuracy climbs again to about 98.5. Finally, we plot the 3 runs side by side from scratch, frozen head, fine-tuned, and save the model. Look at that gold bar. Standing on giants beat building alone by a mile with a fraction of the work. That's transfer learning. Next time we go past what's in the image and ask where, bounding boxes, masks, object detection and segmentation, see you there.